All right, thank you very much for the invitation to speak at the seminar. So I will talk about the joint work with Arguz, which is available on arXiv since 2 months. And in this talk, I will describe a relation between two topics, which are two counting problems. So the first one involved Donaldson-Thomas invariants. So these invariants have some geometric origin. So in geometry, they are supposed to be counts of geometric objects on a Calabi-Yau threefold. So if you have X Calabi-Yau threefold, let's say Keller manifold, dimension 3 with trivial canonical class, then you might want to count things like holomorphic vector bundles. Of a given topology, let's say with given chain classes. And more precisely, you might want to count stable holomorphic vector model for an appropriate notion of stability. So this thing is what you do if you do really complex geometry. You are counting holomorphic object. Or if you are doing symplectic geometry, if you view X as a symplectic manifold, you might want to count Lagrangian submanifolds of a given homology class. And maybe more precisely, there might be an analog of the stability on the holomorphic side. You might want to count spatial Lagrangians, where spatial is defined with respect to the holomorphic volume form on your Calabi-Yau. So these things are two geometric problems you might try to make sense of. And these two problems are related by mirror symmetry. If you do one on one Calabi-Yau, it's related to the other on the other Calabi-Yau. So today I will do neither of them because both of them are extremely complicated. So today I will work with some algebraic time model. So today we'll use some algebraic time model, which involves counting stable quiver representations. So I will spend some time describing what they are. And in some way, some elementary setting, we'll do some linear algebra, hook up moduli spaces out of these problems in linear algebra and extract numbers out of this moduli space. But they should really be viewed as toy model for these more interesting geometric problems. So it's like one side of the, it's like one half of the talk. And the other half will be a relation to a different counting problem, which involves counting holomorphic curves. So Gromov-Witten like invariants. And we will do that in some toric varieties. So I will need to explain that on the first side, there will be a combinatorial object called a quiver, where we will do the Donaldson-Thomas count. And on the other side, there will be a toric variety, where we will do some Gromov-Witten count. And it's important that if you were going to do some geometric case where you are starting with a Calabi-Yau threefold, in general, the corresponding variety where you should do the count of curve is not a threefold in general. It's a much higher dimensional variety whose dimension is actually related to the number of complex moduli of your Calabi-Yau threefold, not the original threefold. Okay, so it's roughly the two topics I want to describe, and I would like to present a precise theorem which compares these two classes of invariants. Okay, so in particular, if you were really doing that in some geometric context, there will be some relation between some count of spatial Lagrangian submanifolds inside the Calabi-Yau threefold and a count of holomorphic curves into a higher dimensional variety, which is maybe geometrically surprising. Okay, so I will start describing in more details what I mean by the first half. So we are fixing a quiver, which is a very simple combinatorial object. It's simply a finite graph with finitely many vertices. And between each pair of vertices, you get finitely many oriented edges or arrows. So I will name by Q my quiver. And once you have a quiver, you have a notion of quiver representation. Given a quiver representation V, it's a collection of finite dimensional complex vector spaces, one finite dimensional complex vector space for each vertex. So finite dimensional complex vector space for each vertex I. And for every arrow in your quiver, some linear map between the corresponding vector spaces. So if you have some arrow going from I to J, you want a linear map, complex linear map from the vector space attached to I to the vector space attached to J. And quiver representations naturally form an abelian category. There is an obvious notion of morphism from one quiver representation to another. It's a collection of maps between the vector spaces which commute with the linear maps attached to the arrows. And so if you had in mind some geometric story, you should think about this category as some kind of maybe model of some kind of piece of either the rough category of current sheaves or maybe of some Fukaya category. Okay, once you have such quiver representation, there is a basic numerical invariant, which is its dimension, which is simply the collection of dimensions of the various vector spaces. So it's just a tuple of integers which live in some lattice that I will denote by capital N, which contain a copy of Z for each vertices I. So if my quiver has D vertices, this thing is just Z to the power D. And so if you're in a geometric context, maybe this Z to the D will be the cohomology where chain classes of your vector bundles live. Or if you're doing counting Lagrangians, it will be the homology group for homology classes of your Lagrangians. And now we want to consider the moduli space. If you fix gamma, a dimension vector, an element in this lattice, you will like consider the moduli space of all possible representations of dimension gamma. So something which will be like your moduli space of vector bundles of given topology of your moduli space of Lagrangians in a given homology class. And in this quiver context, this moduli space is extremely simple. What does it mean to give a quiver representation? It means that for every arrow from vertex I to vertex J, you give yourself a linear map. So there is simply a vector space of linear map from a vector space of dimension gamma I to a vector space of dimension gamma J, if gamma as a component of gamma I. So given linear maps, it's just given matrices. So I just have vector spaces of matrices. But I'm really considering a representation up to isomorphism. And this means divided this space of matrices attached to arrows by the action of some group which is a product of general linear groups attached to the vertices. So for each vertices, I have the general linear group. And essentially, this product of group acts on these matrices by multiplication either to the left or to the right. Okay, so there's a big vector space and a group acting on it. And what you care about is the quotient. So this thing is a description of the moduli space as a set. And as an algebra geometric objects, in general, this quotient will be some kind of Artin stack because you're quotienting by some kind of big positive dimensional groups. And so if you want to get a more reasonable algebra geometric object, such as a nice algebraic variety, we need to restrict the class of objects that you're considering. You need to introduce a notion of stability and restrict to stable or semi-stable objects. So how do we do that? We introduce King's stability. I will consider M the dual lattice of M of n, so the linear form on n with integer coefficients. And I will denote by MR the corresponding real vector space. So simply real valued linear forms on the lattice of dimension vectors. And if I have an element in the dimension vector in n, there is a corresponding dual hyperplane inside MR. It's simply the linear forms which are 0 on these vectors. And a point in this dual hyperplane will be what I will call a stability parameter. And if I fix such stability parameter, I can define what it means for a representation of dimension gamma to be theta semi-stable. So if V is a representation of dimension gamma, we will say that V is theta semi-stable if theta of dimension of V prime is less or equal to 0 for every V prime sub-representation of V. Okay, so it's just a constraint on the possible sub-representations. And so if you are in a geometric context, if you're working with holomorphic vector bundles, for example, you can think of the choice of theta as being the choice of a Keller class or a non-pole line bundle. And then you might have notion of stability like Gieseker stability for holomorphic vector bundles. Or if we are going to count Lagrangians in a Calabi-Yau threefold, if you pick holomorphic volume form, it gives you a notion of spatial Lagrangian. You have a spatial Lagrangian condition. And you should think to this theta semi-stable object as being your spatial Lagrangian guys.
Sorry, Pierrick,
Yes.
Can you explain what you mean by V prime contained in V?
Okay, so these representations from a category, so it's like a sub-object in the category. So very concretely, V is a collection of vector spaces attached to the vertices.
And maps.
And maps.
Yes.
So I have a collection of VI and F alpha. And for V prime, I have VI prime and F alpha prime.
Mm-hmm.
So what I mean is that there are inclusions Fi prime inside Vi, which are compatible with the maps. So okay. I have Vj prime, Vj, I have maps F alpha prime, F alpha, and I want this square to commute.
Okay, thanks.
So indeed, it crucially depends on the maps. I don't know if I can make one very quick example. If you consider this quiver with two vertices, one arrow, and if my dimension vector is 1 and 1, and so my V consists of one-dimensional vector space here, one-dimensional vector space here, a non-zero linear maps between them. then the simple exercise is that if you consider this representation like that with 0 here, C here, and 0, and you embed 0 in C and C in C, this thing is a sub-representation. But if I do this one, this thing is not a sub-representation. If you go through the square, you see there will be a problem. Yeah, roughly, if I take a non-zero object, it goes to something non-zero here, right? It goes to 0 here and not here. So there is really some kind of asymmetry having to do with arrows. Okay, and so in general, theta semi-stability, somehow you constrain your objects by constraining their possible sub-representations. Okay, so we will consider the moduli space M gamma theta, which is a moduli space of theta semi-stable representations of dimension gamma up to isomorphism. And now this thing is very nice. It's really a nice quasi-projective variety over C, which can be constructed by geometric invariance theory. Another way to say it is that if you consider all possible objects, you get this kind of very big quotient. And picking the stability theta is one way to define a quotient in the geometric invariant sense. Actually, you can rephrase it as a symplectic quotient if you want. And you get, by doing that, some honest algebraic variety. So actually, this variety is compact, it's projective. If the quiver Q is acyclic, meaning there is no oriented cycles inside your quiver, and if Q contains oriented cycles, so if there is a collection of arrows forming an oriented cycle, there is a slightly richer story. You can pick a potential W, which is a formal linear combination of oriented cycles in your quiver. Okay, so you can consider finitely many oriented cycles, and you formally consider a linear combination of them. And if you make such a choice, you can get a function on your moduli space, a regular holomorphic or actually algebraic function, which is given as follows. If I have a representation, for every arrow, I have some linear map. And so if I have a cycle, I can compose the corresponding linear maps and get some endomorphism of a fixed vector space. And then I can take the trace of this endomorphism, and I get a number. So that way I defined a function on my moduli space. And now the Donaldson-Thomas invariants, TT invariants, omega gamma theta. So they depend on this discrete parameter gamma, which is a dimension vector. And they depend on this continuous parameter theta, which is a stability parameter. There are virtual counts of critical points of this function trace W on this moduli space. So if you are in a case where this function really has finitely many non-degenerate critical points, these omega gamma theta will be an integer simply counting these critical points. And in general, it has a more complicated looking definition. I will not go into the detail of it, but roughly in general, if the moduli space is non-trivial, it will be some kind of topological Euler characteristic of the moduli space valued in some appropriate, let's say, constructible sheaf, which is obtained by taking the vanishing cycle functor for this function trace W applied to the intersection cohomology sheaf of this moduli space. So roughly, if the moduli space were smooth, and for example, if the function was 0, this thing would just be the topological Euler characteristic of the moduli space. And if the moduli space happens to be singular, you replace the constant sheaf by the intersection cohomology sheaf to get better properties. And if you have a non-trivial function, you incorporate this function by taking this vanishing cycle function. Okay, so I will not go into the detail of this definition, but it's one way to extract an integer out of, so here we are fixing a quiver, a potential, a dimension vector, and a stability parameter. Okay, so historically, the story of Donaldson-Thomas invariants come from considering the case of holomorphic vector bundles, and from the fact that holomorphic vector bundles on a Calabi-Yau threefolds, you can view them as critical point of some functional, the holomorphic Chern-Simons functional, on the infinite dimensional space of 0-1 connections. So on the Calabi-Yau threefold, you can view holomorphic vector bundles at critical points of some function of some infinite dimensional space. And the original geometric Donaldson-Thomas invariants are defined by counting these critical points. And so here we just have a very simple finite dimensional version of that. If you have a quiver with potential, you have a finite dimensional moduli space, a finite function, and you might try to count the critical point in an appropriate way. Okay, so these things are integers, but to write down formulas, it's actually easier to work with so-called rational invariants, which are defined by an explicit formula. Roughly, you sum over all possible ways to write the vector gamma as a multiple of another gamma prime in the lattice n, and there is a combinatorial factor and omega. So actually knowing all the omegas or knowing all the omega bar is exactly the same. It's just that to write some formulas I will write down in one moment, working with these rational numbers is actually much easier than working with these integer numbers. Okay, so even in these simple quiver contexts, these numbers have a long story. They have been essentially defined originally by Kontsevich and Sobelman, Joyce and Song. And the definition I'm using here is some reformulation due to Meinhard, Heinecke, and Davison and Meinhard. Okay. So the key property of these invariants is the fact that they are functions of this continuous stability parameter theta. So I recall that theta was living in this real hyperplane, living in this real vector space. So I have some real hyperplane, gamma perp. And these things are integers. And so if the integers depend on a continuous parameter, you will typically get some wall crossing phenomenon and jumping behavior picture. So what you'll have is inside this hyperplane gamma perp, there will be various chambers. And as long as theta remains inside one of these chamber, this integer omega gamma theta will remain constant as a function of theta. It does not change this. But when you go from one chamber to another, then you might have stable objects which become unstable, or vice versa. So the topology of your moduli space M gamma theta will change. And in general, your DT invariant omega gamma theta will jump discontinuously from one chamber to another. So you have some wall crossing story. And this wall crossing behavior is captured by some universal wall crossing formula, which is due to Kontsevich and Soberman. So it's a formula that you can prove in the context of this quiver representations, but which is expected to hold if you're able to make sense of the geometric counting problems. Yes, I will not write down this formula, but I will try to explain what you can do with it. You can use it to express, so you can use it to express general DT invariants omega gamma theta in terms of simpler so-called attractor DT invariants. So to define what they are, I need an additional object. So recall that n is a lattice of dimension vector, one copy of z for each vertex. And my space of stability parameter is a space gamma perp inside MR, which is made of linear forms on n. And from the combinatorics of the quiver, I can define a skew symmetric form on n that I will denote by omega, which is defined by omega of the basis vectors Eij is equal to Aij minus Aj, where Aij is equal to the number of arrows from I to j in the quiver. So this thing is a skew symmetric form. And if you were in a geometric context of, so here let me write, if you had some Calabi-Yau threefold, and if you were going to count spatial Lagrangians, Lagrangians will have some class in H3 of your Calabi-Yau. And on the H3 of your Calabi-Yau, there will be some intersection form. And because we're in odd dimensions, this intersection form will be skew symmetric. So here in our quiver context is a skew symmetric form is the analog of the intersection pairing if we're going to deal with Lagrangians in a Calabi-Yau threefold. And now I can use this skew symmetric form to produce a canonical stability parameter.
Sorry.
Yes, sure.
Technical question. Do you, in general, I guess it's an earlier question. In Q, do you allow loops?
Sorry.
Do you?
I think I allow loops. So indeed, okay. And so if there are loops, I do not really. Okay, let me see it. Yeah, it's fine. So I would just get. Yeah, I allow loops. Yes.
Okay, thank you.
Okay, so using this omega, if I have gamma in n, I can simply evaluate omega on gamma. I can look at the contraction of omega with gamma to get a linear form in the second entry. So this thing is a linear form in n, so it's an element in M. And actually, it lives in the hyperplane gamma perp because omega of gamma and gamma is 0, because gamma is Q symmetric. So using this form omega inside the space of parameters gamma perp, I've produced a special point which is omega contracted with gamma, and I will call this special point the attractor point. And I will define the attractor DT invariant that I will denote by omega gamma star as being the DT invariant at the attractor point. So this thing is attractor DT. Then maybe I can make a comment in the geometric situation. So actually, the attractor terminology comes from some physics story involving black holes and supergravity. And if you are going the geometric story of considering X a Calabi-Yau threefold, and if you pick a homology class in H3, so which would be the class of the Lagrangians that you care about, then the space of stability parameters should be something like the space of complex structures on X, which is some space of complex dimension equal to the Hodge number H12 of your Calabi-Yau. And then this should be special loci inside here, obtained defined by the following attractor condition. So your class gamma, okay, by Poincare duality, I can really view it in H3, in H upper 3 in the cohomology, and this thing as a Hodge decomposition. And then you might look to the condition that this class of your Lagrangian is purely, okay, let me say it like that. You can ask that gamma, that the H21 piece of this class is equal to 0. Okay, so your class, I can decompose it according to the Hodge decomposition. And I can ask that the H21 piece is 0. So roughly this thing should give me H12 conditions. And I have H21 parameters for the complex structures. So if this thing were like independent conditions, I would expect to get a 0-dimensional locus, maybe a bunch of points inside the moduli space of complex structures where this condition is satisfied. So I guess in general, for like concrete geometric Calabi-Yau, I actually have no real idea what. So actually for special cases, there are a few results, but in general, I don't really know what to say about this locus. But it is a geometric, it happens to be the geometric version of what I'm talking about in this quiver context. I claim if you care about Lagrangians on the Calabi-Yau threefold, they are like very specific complex structures, which are like should be isolated, defined by this condition, Hodge theoretic condition.
I have a quick question. So
Yes.
is the homology H3 corresponding to the lattice N or M in the geometric setting?
Yeah, so I think really the homology should be N, I think.
N, okay, thank you.
Yeah, but actually in the geometric setting, the pairing is very non-degenerate, so I can reuse it to identify N and M somehow.
Yeah.
But yeah, let's say it's really N. So if I come back to the case of Quivers, why do we care about this particular attractor DT invariance? is the fact that in many cases they are much simpler than the general invariants. So they are often simple. For example, if Q is acyclic, does not contain any oriented cycles, then omega gamma star is equal to 0 if gamma is not one of the basis vectors EI, and is equal to 1 if gamma equal to EI. Okay, so they are essentially all 0 except the obvious one, which are equal to 1. Okay, gamma equal to EI correspond to representation where I have a single one-dimensional vector space on the vertex, and all the other vector spaces are 0 and all the arrows are 0. In this case, it's obvious the Modi space consists of a single point. The corresponding invariant is just 1. And so for the attractor invariants, all the others are 0. There is nothing else. And there is a conjecture. Let me say Montgomery-Pillin, which says that in more interesting geometric examples, they are still simple. For example, if I take a toric Calabi-Yau threefold, then you can cook up a quiver with potential whose categories of representations reproduce the derived category of current sheaves on X. So here I'm not doing special Lagrangian, I'm doing the mirror version involving holomorphic vector monoids or current sheaves. So for this kind of non-compact toric Calabi-Yau threefold, actually these categories have a description in terms of a quiver with potential. And the prediction is that for this particular quiver with potential, the attractor invariants are also extremely simple. So they are essentially all 0 unless gamma is EI or gamma live in the kernel of this skew symmetric form. And just to mention, this conjecture is known to be true. It's true, for example, for X equal local P2, the total space of the canonical line bundle on the projective plane. And this thing is somewhere, it is contained in a recent paper I wrote with Descombes, Lefloc, and Pillin, where you study really like the geometric Donaldson-Thomas invariance, so on the holomorphic vector bundle side, in this non-compact Calabi-Yau threefold geometry. Okay, so in general, these attractor invariants are particularly simple. And now, essentially, by word crossing, you can express a general DT invariance in terms of these attractor invariants. And it is really these formulas that I care about. I can write the general DT invariant for any theta as a sum over all possible decomposition of gamma into gamma 1 plus gamma r, a sum over trees that I will describe in one moment, a coefficient which depend on the tree and on the elements in the decomposition, some coefficient which are some integers, and then some product of the attractor invariants attached to the various elements of the decomposition. Okay, so essentially from the word crossing formula of essentially applying many times, you can get such formula expressing the general DT invariant in terms of the attractor DT invariant. And the formula takes the shape of a sum over trees, and each trees contributes some multiplicity, which is some integer. And it is really these integers that we care about. So let me briefly try to explain what are these trees. So essentially, we'll move in the space of stability parameters. So we start with the stability point theta, which is the original point that we care about, contained in the hyperplane gamma perp. And starting from this point, you can try to move towards the attractor point. So you can try to move in this direction where you contract omega with gamma. It is a preferred direction inside the upper plane gamma perp. And so locally, nothing happened, your invariant remained constant. But at some point, you might hit a wall. And you will hit a wall along places where other hyperplanes, for example, there might be another hyperplane gamma 1 perp, or maybe another hyperplane a gamma 2 perp, which intersect gamma perp along a common locus here. So for example, this thing could correspond to a decomposition of gamma into gamma 1 plus gamma 2. Okay, so if gamma equal gamma 1 plus gamma 2, the place where gamma 1 perp intersect gamma perp, then gamma 2 perp also intersect. And then this thing corresponds to a wall, so you can have a wall crossing. Particularly, your object of class gamma could split, your stable object would become unstable and become an extension of an object of a stable object of class gamma 1 and a stable object of class gamma 2. And this phenomenon will be graphically captured by a tree where I continue inside the hyperplane gamma 1 perp in the direction omega gamma 1, and I continue inside the hyperplane gamma 2 perp inside omega gamma 2, and so on. So I might hit other walls, and these trees capture essentially all the possible things which could happen to your stable object when you move along these trajectories. Until at some point you just arrive in some attractor chamber and then you go forever at infinity. And so if here, for example, I have some attractor point corresponding to some gamma I in some gamma I perp, then you just continue forever at infinity. And here the corresponding invariant is just the attractor invariant omega gamma I. Okay, so in general, I have this formula, I have a kind of sum of the big trees. And these trees somehow capture the combinatorics of the wall crossing which can happen. And each tree contributes some integer, which is some kind of, which somehow capture like the contribution of this tree in the wall crossing formula. And maybe some comment, some geometric comment is that if you are going some geometric story involving, for example, spatial Lagrangian, this thing will say that if you start with a spatial Lagrangian, and if you move the complex structure, maybe at some point your spatial Lagrangian will become unstable. I mean, your Lagrangian will cease to be spatial Lagrangian. And one way it could happen is that your Lagrangian could become singular with two components which are individually spatial Lagrangians. And then these kind of vertices of the trees capture how essentially from elementary spatial Lagrangian, you can build up bigger spatial Lagrangians. It's a kind of basic picture. Are there any questions about this formula or this picture?
Yes, in the Lagrangian case, does
Yes.
this correspond to a surgery of the class gamma 1 and gamma 2, or of the spatial Lagrangian gamma 1 and gamma 2 somehow? Or?
Yeah, I would guess so. I'm not sure exactly which kind of, but yes, some kind of surgery, yes.
Okay.
So maybe like in the simplest cases where the kind of the elementary attractor thing are just one, maybe you start with simply like Lagrangian 3 sphere, which are like very like spatial Lagrangian 3 sphere. And then, yeah, so maybe it's one way to think about the quiver in the simplest possible context. If in your Calabi-Yau threefold, you have a bunch of spatial Lagrangian 3 spheres. So they are like isolated because 3 sphere is a 0 first bit in numbers. So they're like rigid object. But two 3 spheres could intersect in dimension 3. They intersect into some number of points, like according to the intersection form. Yeah, and then by probably some kind of surgery around the intersection point, you can glue these 3 spheres together to produce more interesting spatial Lagrangians. It's a kind of the basic picture. And some of the, like the arrows in the quiver, some of the captures is intersection points between the various three spheres. And it's expected that this kind of elementary linear algebra of the quivers is a good model of what should happen for special Lagrangians.
Okay, thank you very much.
So indeed, for special Lagrangian, most of what I'm describing, as far as I know, is conjectural. But we can do this algebraic model involving this quiver. Okay. So the main point, like the main result of our paper, is to give a completely different interpretation of these coefficients. So essentially, we interpret these integers as counting holomorphic curves in some different geometry. And the basic reason for that is that these trees, which here capture possible wall crossings, they look a lot like tropical curves. They look a lot like as capturing degeneration of some holomorphic curves. And it is what we prove, that you can really interpret these graphs as tropical limit of some holomorphic curves in some geometry. And the multiplicity attached to the tree will be exactly a count of holomorphic curves with given tropicalization. So the point, some of the key point is that these trees have two different interpretations depending on how you look at them. In one way to look at them, they capture the wall crossing phenomenon, how stable objects become unstable, or in this picture of Lagrangian, how you do surgery to cook up complicated Lagrangian for a simple one. But you can also use these trees as coming from algebraic curves, holomorphic curves. So we will count holomorphic curves in some geometry. So I need to tell you which geometry in some toric variety, which will be of complex dimension D, if D was the number of vertices of my quiver. So in particular, if we're going to consider a geometric story involving a Calabi-Yau threefold, probably you should count curve into a geometry of complex dimension equal to the number of complex structural deformation of your Calabi-Yau threefold. Okay, so in particular, the count of curve I'm talking about are not at all curves in the Calabi-Yau threefold. They are curves in some kind of auxiliary geometry of much higher dimension in general. Okay, so in this quiver context, we have a simple combinatorial description of what this variety is. I will simply write down a fan inside the real vector space MR. So, and I want to pick a fan, a sigma, containing the rays spanned by the attractor direction omega gamma I. Okay, so this construction will depend, I fix gamma, and I fix a decomposition of gamma into gamma 1 plus gamma R. Okay, so from this gamma I can cook up some rays inside this vector space MR. And I just complete these rays into a fan, into a union of cones in MR. So here are some choices for how to do that, but the choices will not matter at the end of the day. So if I really want, if I subdivide a lot, I can really produce a fan, which is a fan which is produce a smooth projective toric variety. Okay, so I built X sigma, some smooth projective d-dimensional toric variety. And by construction, so it's a toric variety, so it's a compactification of the torus C star to the D by adding some various toric divisors. The divisors are in one-to-one correspondence with the rays of the fan. And so here I have special rays corresponding to the elements gamma I. So I have special toric divisors, D1, D2, D3, where Di is a divisor corresponding to this ray. And now there is a last thing that I need to set up my enumerative curve counting problem. Inside each of these toric divisors, Di, I will define a hypersurface, Hi, by an explicit equation. I will consider z to the power gamma I divided by its index in the lattice n equal to some generic constant Ci. Well, you see the equation on Di. Okay, so maybe I will not go into the details. Just out of the gamma I, by some explicit equation, I can cook up, so this thing is some hypersurface in Di, but Di was already codimension 1. So this thing Hi is really codimension 2 in the ambient toric variety. So for example, here on this picture, where I draw a two-dimensional toric variety, this Hi will simply be points on the toric boundary. Here I will have some H1, H2, H3. Okay, so I just have a bunch of points on the toric divisors. If I try to do a picture in higher dimension, I have toric divisors, so I have various surfaces compactifying C star squared. And inside these various surfaces are various curves, H1, H2, H3. Okay, now I can describe a moduli space of holomorphic curves in this geometry. I will consider M, the moduli space of rational curves, so F. It's a genus 0 curve with R+1 mark points to my toric variety. And I impose the following condition. I impose that my curve in the toric variety intersects the toric boundary only at the mark points P1, PR, PR+1. So I want the preimage. Okay, I denote by boundary of X sigma for the union of toric divisors. I want this thing to consist exactly of the point P1, PR to PR+1. And in addition, I want the mark point Pi to be contained in this locus Hi for every I between 1 and R. And at the point Pi, I want the contact order of the curve with the divisor Di to be equal to the divisibility of this attractor point in the lattice M. Okay, so omega gamma I is a point in this M, which is Z to the power D, and the divisibility is just a maximum integer, such that this vector is a multiple of that in the lattice. So it's just some fixed integer. Okay, so let me try to do a picture where I'm counting curves, which generically are contained into the torus. And at various mark points, the curve is hitting the toric boundary, and the position of these points are constrained to be on this hypersurface. And we have various contact order which are also prescribed at this point. So P1, P2, P3. And here I have PR+1, so I have a last extra point, which is required to go somewhere on the toric boundary, but I do not specify where it should be. It's a kind of the basic, we consider the moduli space of all such curves. And maybe from a symplectic geometry point of view, one should really count not closed curves. So here I'm really counting closed algebraic curves. Maybe one should really be counting disks. So with a boundary, and so maybe your disk should look like that. But as I'm not really good with disk, and we'll use some algebra geometric technology, this closed curve somehow you should think about as being obtained by closing up this boundary by gluing some small disk on the other side to get a closed curve. Okay, so we have this moduli space of curves, and then we say something about this moduli space. This moduli space has dimension, as expected dimension, d minus 2. You can do some Riemann-Roch computation. You will give the expected dimension of this moduli space. So in particular, if we were in dimension 2, then this moduli space would just be 0-dimensional. It would be hopefully some bunch of points, and we could just count these points to extract some Gromov-Witten-like invariant. But in dimension 3 or bigger, this moduli space really has positive dimension. So I need to do something to extract numbers. And this is related to the fact that this moduli space M is not compact. Because here I'm assuming the curve is generically away from the toric boundary and intersects the boundary in finitely many points. But if the curve can move in a non-trivial family, in general, the curve can degenerate, and the natural limit might be actually contained inside the toric boundary. And when I do that, for example, this condition of having given contact order at a given mark point, if my curve does not intersect properly the toric boundary, this condition no longer makes sense. So I need to compactify the moduli space by allowing holomorphic curves, somehow going to infinity of the torus and falling into the toric divisors. And there is a way to do that. There is an algebra geometric way to define such a compactification. There's a nice compactification number obtained as moduli space of stable log maps, as developed by Gromov-Witten and Gross and Zieberg. Okay, so in general, there is this topic of log, a Gromov-Witten theory, which exactly considers this topic. You have a variety with a normal crossing divisor, and you're interested in the holomorphic curves in this variety with intersecting these divisors in a bunch of points with a bunch of contact orders or tendency conditions. And this theory is about producing nice compactification of these moduli spaces, dealing with the difficulty that the curve might fall into the divisor. Okay, so I will not go into the technology involved in the definition of this moduli space. I will just try to make a picture of this moduli space, a very rough picture of the moduli space, which is that the moduli space itself, at least virtually, if I forget all usual issues with moduli space of holomorphic curves, if I pretend that everything is as nice as it should, then this moduli space is itself some kind of normal crossing compactification. I have my moduli space M of nice curves, and then I produced this compactification by adding divisors at infinity. And these various divisors naturally produce me a stratification of the moduli space. In particular, inside this moduli space, I have some kind of maximally degenerate strata. I have 0-dimensional strata where d minus 2 divisors intersect, let me say, transversally. Okay, so if really M has dimension d minus 2, and if I compactify it by adding various divisors, and if it's really normal crossing, if all the intersections are transverse, I will have various strata correspond to various intersections of various divisors. And I have the smaller strata, zero-dimensional strata, corresponding to intersection of d minus 2 divisors. Okay, for example, if this picture were a toric picture, then this point will be the torus fixed points of the toric variety. Okay, and essentially we'll extract numbers from counting the zero-dimensional strata. Okay, the moduli space has positive dimension, but we'll count the maximally degenerate curves, which correspond to the zero-dimensional strata inside this normal crossing compactification. And actually, the various strata of this moduli space have their combinatorics have some combinatorial description in terms of tropical curves. So I claim that to each strata of the moduli space M, you can attach to it a family of tropical curves in MR. Roughly, if you have a curve to your toric variety with a toric boundary, if I really look at the curve in the boundary of the moduli space, the curve might be very degenerate. And my general zero curve could have many irreducible components. And this curve maps to the toric variety with boundary. And the various components of my curve, could map into the various boundary divisors. And I could capture the combinatorics of what is happening simply by drawing dual intersection complexes. Okay, out of my curve, I can draw a graph by taking one vertex for each component, one edge for each node. And if I similarly consider dual intersection complex of the toric variety, I will exactly get the fan. So here I get the fan of the toric variety in MR, and I get a tropical curve, which is essentially a map from this graph to this real vector space, satisfying various properties. And the zero-dimensional strata that we care about, their combinatorics is captured by d minus 2 dimensional families of tropical curve. So here it is a key point that this tropicalization operation is really some dimension reversing operation. It's exchanged because we take a dual picture. So here zero-dimensional strata in the space of curves correspond to like families of tropical curves.
Sorry, Pierrick. So,
yes.
So it's been already 1 hour that you've been.
Yes. So I will.
But you can. I don't know. How long do you?
Yeah, in 5 minutes I will be done.
Okay. All right.
So here I essentially arrive at the point, which is what is the connection between the zero-dimensional strata and some kind of trees. Okay, so now I can arrive at the result and conclude. So in this quiver story, we had some tree like that. And the remark is that these trees, you can naturally deform them in d minus 2 dimensional families, because the starting point of this tree is living into an hyperplane, so I can move it anywhere inside this hyperplane and just deform the tree accordingly. And you can show that the tree can deform. And because moving the point in the direction of this edge is like mainly doing nothing, you already get a d minus 2 dimensional family of tropical curves. So given a tree T, you can cook up rho T, a d minus 2 dimensional family of tropical curve. And now you can define a Gromov-Witten type number, which is counting zero-dimensional strata in the moduli space, let me say with tropicalization, rho t. Okay, so this curve is a very degenerate curve. The curve has broken into many components, and the kind of combinatorics of that is captured by the trees. Like the various vertices of the trees correspond to the various components of your curves, and the way your tree is embedded inside RD tells you how does this component maps to the boundaries of your toric variety. And this number is a count of like real, like of honest geometric curve with given combinatorial type. And now the theorem is that these coefficients ft, these kind of universal coefficients appearing in the wall crossing formula, giving me the contribution of a tree, is actually exactly this Gromov-Witten count. And so you can view this theorem both ways. You can view it as giving some enumerative meaning to these invariants, which express the wall crossing formula for dt invariants of the quiver. Or if you view it another way, in some way, you can view it as a way to compute this Gromov-Witten invariance, because this coefficient, you can compute it in some kind of algebraic or combinatorial way. So you can use this result both ways. And just so really the key technical content of our paper is to prove the correspondence theorem, to prove that these Gromov-Witten count of curves really are counting by these tropical trees with these correct multiplicities. And so there are many results of this type, like tropical correspondence theorem, going back to Mikalkin and Nishnu-Zibert. And here the main innovation is that our correspondence theorem involves this kind of non-trivial strata inside the moduli space. And at the tropical curve level, we have families of tropical curves. And the usual theorem, which have been proved before, involves the case where the moduli space is zero-dimensional, you have finitely many curves. Algebraic curve, which correspond to finitely many tropical curves. But here, in this problem, you have a non-trivial moduli space. You have families of tropical curves, and zero-dimensional strata correspond to families of tropical curves, and somehow we need to deal with that. And in particular, we really need to use this kind of log Gromov-Witten technology to prove this result. Okay, sorry for being a little bit over time. I will stop there. Thank you for your attention.
Thank you. Any question?
So I have one. So the count is rather combinatorial. Do you genuinely get integer numbers?
Yeah, so here, yeah, so you really get integer numbers. And actually you can show that, yeah, really these Gromov-Witten counts, if you're doing, actually it's not as bad as it sounds. If you really do it properly, if really the CI are general enough, you can really show that they are enumerative. So that they are really, I mean, here I was a bit imprecise when I say, okay, I say count zero-dimensional strata. And actually, it's really true. It can be defined as a count of zero-dimensional strata. So maybe in general, you might have some kind of, on these moduli spaces, there are various virtual classes, and you might give some kind of virtual definition of these counts. But actually, you can really show that they are really enumerative. So actually, I'm lying a little bit, which is that in this statement, actually, there is some coefficients that I did not explain. And it could be that maybe these curves are enumerative, but maybe they have automorphisms. So maybe actually they produce rational numbers, but actually there is some kind of correction factor, and at the end you get some integers.
So even if you do have automorphisms, you have some clever way to cancel them out.
Yeah, that's right. Somehow there is some kind of universal thing to multiply by, which somehow produce an integer at the end. So really at the end, this thing is really an integer.
Cool. Thank you.
Also have a basic question, Pierrick.
Yes.
So thanks for the talk. So you said you look at one of these trees T, right, which corresponds basically to the coefficients that you're going to count. I didn't really understand the relationship between, because there's also a tree that describes the tropical curves, right?
Yes.
Is there any relationship between the tree describing the tropical curves and the tree T?
Yeah, that's right. So here I tried, maybe it was a bit quick example, that given a tree T, you can view it really as a tropical curve. But I don't know if your question is like, is there more like conceptual explanation for why it should be like that? Or
Yeah, some more intuitive.
yeah, that's right, because here it's some kind of, the point of this correspondence, that it's some kind of miracle that you have the same combinatorics, which can be interpreted both ways, like both as the trees from wall crossing or the trees coming from tropical curve. And in general, I don't have, okay, it's not. Okay, maybe I can try to say something, probably it will not be really helpful, but I claim in some very specific cases, you can get some kind of geometric understanding of the relation I've been talking about. So on one side, if you believe the geometric story, maybe you should be dealing with special Lagrangians. So yeah, maybe there are special Lagrangians. And assume that for some reason, your special Lagrangian in your Calabi-Yau threefold, actually you can construct them from some special Lagrangian in one dimension less, in some maybe holomorphic symplectic surface, let's say hyperkähler real complex dimension 2. Let me assume that. So let me assume that we're in complex dimension 2. And in this kind of hyperkähler context, there is a natural way to go to special Lagrangian to holomorphic curve. You might want to do some kind of hyperkähler rotation. Where you change the complex structure, and then your special Lagrangian might become some kind of holomorphic curve. And I claim that in a very specific geometry, this picture is actually what is happening and is some kind of explanation for the correspondence I've described today. But you see, this kind of thing has only a chance to work if this geometry I'm counting curve is a very small dimension, so that it can be related to the original geometry by some geometric operation. So yes, so actually, yeah, there is a very nice story related to mirror symmetry for local P2. Maybe I don't have time to explain, but let me say that for this very specific story, you can understand this passage from holomorphic curves to special Lagrangian in terms of some kind of hyperkähler rotation. And in general, I cannot do that. And so in general, if we want some kind of like more conceptual explanation for why such relation should be true, the only explanation I know is it's some kind of string theoretic explanation. Like, let me say physics-like explanation. And I guess a few months ago, I wrote a paper which contained the title Holomorphic Flow Theory. Which contain a lot of speculations, which are supposed to explain this kind of correspondence, and which also uses this correspondence as motivation for new speculations. For example, on this DT side, the invariants are naturally holocharacteristic, but holocharacteristic you might opt to categorize them, like upgrade them to some honest vector space, the cohomology of the moduli space, which suggests that this kind of curve should have some kind of upgrade, some kind of categorification, which is maybe not something you expect usually in Gromov-Witten theory. And the speculation, it is what you expect if you count curves in some holomorphic symplectic or hyperkähler setup. And here I should point out, here I was in a toric variety, which maybe does not sound really hyperkähler, but actually I had these omega, which give me a Poisson structure here. And so really the holomorphic symplectic geometry as a Poisson, as a symplectic leaves of these holomorphic symplectic form on C status.
Okay, thanks.
More questions? Doesn't seem so. Okay, so thanks again, Pierrick.
Thank you very much.